materials. So that is why I think you need to learn almost all sorts of materials. Good afternoon. So, I am continuing the lecture with the previous session. I think we discussed already that there are polycrystalline materials and also single crystalline materials, and there are glass. So, as we can see, there is a microstructure of the polycrystalline materials. So, these are all called grains, and there are grain boundaries. So, in case of single crystal material, there will be only outer grain boundary. There will not be any. There will not be many grains. There will be only one grain. Okay, and as you can see, the fracture surface of alumina, where you can see these are three-dimensional view of individual grains, and you can see that there are intergranular spaces or voids, as well as you can see the grain boundaries, and also you can see there are grain pull out, and even you can see the some kind of transgranular fracture as well as intergranular fracture. So these are different natures of the failure in the crystalline material. So as I said that there are quartz and the glass. Quartz is the crystalline phase of the silica, whereas glass is the liquid phase, which is a super cooled liquid. So there are another type of materials called solid solution. So as we know that alloy is one such example. So like in liquid solution, we know we add the sugar into the water, and sugar dissolves and it goes interstitial site of the solvent molecules. So similarly here, in case of solid solutions, so there are solvent. So the major phase is a solvent, and there is a secondary phase, which is a secondary element, which is called solute. So always solute will be dissolved in the solvent. So as you can see, green color one is the solvent and blue color one is the solute, and solute will be dissolved in the solvent. And as you can see from the microstructure or the cartoons, that for the substitution on solid solution, the solute is substituting the solvents. Similarly, in the interstitial solid solution, as you can see, that solute is actually taking the gap between the solvents. So the solute has to be small enough to fit into the specific gap. So this is a substitution on solid solution, and this is an interstitial solid solution. So there are examples like zinc in copper for brass, and carbon in iron in case of interstitial solid solutions. So these are alloys. So when these two metals have significant difference in electronegativity, if these two alloying elements has significant difference in terms of electronegativity, instead of forming the alloy, they form compound. So that is called intermetallics. Okay, they are like a compound, they are intermetallics. Intermetallics will have different properties, less ductility than alloys. Okay, so there are different four conditions for substitution of solid solution formation. This is postulated by Hume and Rothery rules. So Hume and Rothery. So one of the rules says the atomic radius of the solute and the solvent should not differ by more than 15%. So they should be, because it's a substitutional, they should not have too much difference in terms of size. or volume or radius, then it will not fit properly into the lattice structure. So that is why, so it is favorable if, and they can form substitution of solid solution if their radius is within 15% difference, and the solute and solvent should have similar electronegativities. Solute and solvents should have similar electronegativities, and individually both the alloying elements should have similar crystal structure while they are in the pure form. Similarly, the maximum solubility occurs when solvent and solute have same valency. However, metals with lower valence will tend to dissolve metals with higher valence. That is also possible, but it is favorable to have similar valency. And we have another class of materials called composite. As we know, in case of composites, we have two phases. One is called reinforcement and another is called filler or matrix. So reinforcement can be of different types, but however, when these two phases are forming the composites, they do not react to each other, they maintain their individual grain boundaries, and they maintain their identities, but they do not completely merge or dissolve. Interestingly, they actually work in a concert. So the physical property, or specifically the mechanical properties of the resultant composite, will be enhanced from the individuals. As we know that beam, for example, rod are the reinforcement and concrete, cements and sands are the matrix, and together their mechanical property increases enormously. So there are different types of reinforcement. One is particulate. So in case of particulate, you can have both reinforcement and the matrix are particulate, and there could be platelet. So in case of platelet, the reinforcement is actually platelet, or even sometimes you can have both platelet matrix as well as platelet reinforcement. I'll give you some examples afterwards. So there could be fiber matrix composite, reinforcement as a fiber, matrix as a particulate. I think one of the finest example is, as we know, in India we make a lot of idols of clay. Even the houses, clay houses we make. So while we are making the clay houses, we mix the jute, straw, chopped into small fibers and mixed with the clay, and then we cast. So this is one of the example where fiber actually hold either side, and if there is a crack formation, crack doesn't propagate. So here fibers actually act like a bridge between the two sides. Similarly, in case of platelet, if you see the nacre, pearl, right? Nacre, pearl. So these are actually platelet composites. And if you see the old days house, I think I'll show you the examples. British period houses, even older houses, you see they have used the tiles for the walls, and they are like a platelets, and in between they are the cements. But in case of nacre, or in case of snails or pearl, so there are platelets, and in between the platelets there are proteins. These proteins are actually act like a shock absorber, and these platelets are intercalated. So they are basically intercalated, so that crack, if they initiate, they cannot go in a straight line, rather they proceed in a zigzag way. So that is how they can act like a reinforcement or toughening. Similarly, in case of particulate, we'll see later on. I think somebody was asking about the composites, zirconia, dental implants. So there we'll see that zirconia is actually a toughening agent, and zirconia is also a matrix. So here we will see zirconia tetragonal phase and zirconia cubic phase both are working in concert, where cubic phase is a matrix and tetragonal or monoclinic phase will be like a toughening agent. I think we will discuss later on in the next session. But as I said, the particulate composite, where you have reinforcement is a particulate, as well as the matrix is particulate. So similarly, in case of fibers, you can have short fiber and matrix, and you can have long fiber reinforcement, and matrix is like resins or any other materials. So there could be short fiber as a reinforcement. I mentioned to you one of the example is the dental fillers. Nowadays composite dental fillers are available, but resins are mixed with short fibers for making composites. People are trying to make the bone using short fiber of glass, ceramics, even hydroxyapatite or any other materials, and then they're using the matrix and they're making the composites. Similarly, for long fibers, I think one of the finest example is in our country, we know Agni missile. So they are using the long carbon fibers, they weave in 6 directions, and they infiltrate with the pitch. They infiltrate with the pitch, and then they go for dehydrogenation and graphitization. And eventually they get the hexagonal block, which they machine into dome, and they get the hemispherical structure. And this hemispherical structure is actually, the structure will be like this, and this is actually the front of the Agni missile. Similarly, you know, aircraft brake is also a carbon-carbon matrix disc, as well as there is another carbon-carbon matrix disc. One is in static condition, another is rotating, and when they are landing, one is rubbing against another, and that is how it works. And whiskers is basically, I think you know the meaning of the whiskers. It is for the cat, right? But whiskers is meant for single crystal ceramic or single crystal fibers. But whiskers nowadays is a carcinogenic material. Usually it is no more encouraged to use for the applications. So I can see here wood is a composite where we have cellulose fibers and we have lignin as a matrix. Similarly, we have this wooden composite, we have even bone and the dentures. So all are naturally derived composite materials. So in case of dentures, we know there are 2 types of materials. One is, can you tell anyone what is one material? One is hydroxyapatite fibers, and there is another one which is collagen fibers. And this is a hybrid composite, and where both are acting as a matrix and reinforcement, collagen and hydroxyapatite. Similarly, in case of bone, but in case of bone, the collagens are unidirectionally arranged, and individual layers of collagens are again arranged in a cholesteric fashion in one of the type of liquid crystalline material, and with that they give you toughening. I think we'll come later on, I'll show you how they work. So this is one of the example of particulate composite. Particles are dispersed in a matrix. And how the reinforcement happens in case of particulate composite? Any idea? So here you will see these 2 particles will have 2 different elastic modulus. Because of this modulus mismatch, they will have differential toughening property. Similarly, in case of fiber matrix composite, fiber could be arranged unidirectionally or multidirectionally, and here fiber actually act like a reinforcement, and fiber matrix interaction is the major cause for reinforcement, where fiber pull out will be responsible for energy absorption. Similarly, we have the platelets as a matrix and as a reinforcement, and we can have matrix. We can have short fibers or whiskers, or you can have sandwiches, like I think already you are sitting on a tables. So these are sandwich structure, and these are actually composites. So while you are considering any of the materials, I think, or you are going for fabrication of any of the materials. So can you think of defect free materials? No, it is impossible. So there will be defects, and these defects act like a stress concentrator, right? I think everybody I think knows. So as you can see that, so there is a defects. The defects could be like circular, it could be like flat, or it could be like notch. And as we discussed, I think already we discussed, in case of metals, we can see that all layers are of same material, same atoms, if it is a monolith. And in case of ceramics, what you can see, you have the alternate structure. So that is why in case of material, you have the notch, but under stress, this notch may be rounded or may not be rounded. In case of metals, there is a possibility of slippage. So one plane can slip from another plane, like in graphite, right? So this notch, which act like a stress concentrator, actually it will be rounded. Then as it is rounded, the stress which was acting on a very small area, which will be divided into larger area, and eventually the stress will be distributed. But in case of ceramics, which is a metal oxides, metal nitrides, metal carbides, so in these cases, as we have seen the structure, that we have alternate anions, cations, anions, cations. So there is not much scope of slippage, there is not much scope of shifting of the planes, right? So that is why they actually break down, because there is no slippage and this notch remains forever. So notch doesn't, there is no scope for this notch to be rounded, and that is why the ceramics always behave like a brittle material, and metal, even they have the notch, they actually be rounded, and that is how the metal will have plastic deformation, and ceramics will not have plastic deformation, and they will be brittle. So that is why the ceramics materials are having very low fracture toughness, if they have a very small defects, right, and they will be growing and there will be failure. And that is why, so these notches are act like a critical stress concentration factor. And as we know that fracture toughness directly proportional to crack length. Okay, so in case of material, the fracture toughness is a material's property, individual material's property. It directly depends on fracture length, and this value of fracture length is very small for ceramics. So in case of ceramics, even if you have very small fracture, very small defects, it can grow and eventually it fails, right? But in case of metals, it will not happen. So that is why even if you have the cracks in the metal, even if you have cracks in the plastics, we still use it. But for ceramics, glass or crockeries, what we do, as you see the notch, we just say you have to throw, otherwise you'll encounter the accident, right? So that is why, so ceramics having low fracture toughness and metal are plastic, there will be plastic deformation and there will be some toughening mechanism. But in case of ceramics, what we have to do, we have to play with the microstructures. We have to play with the microstructure to make it tough. So as you can see here, there is a glass, this is ordinary glass. So what will happen? The glass, how do you know what is the microstructure of the glass? Which is isotropic, there is no grains. So that is why in case of ordinary glass, the crack always almost follow the straight line, and the crack propagation will be at the velocity of sound. I think you might have heard some noise, crack, You see, there are two pieces gone. So that is why in case of ceramics, specifically for glass, there is a catastrophic failure. So vehicles or even aeroplanes, so they use the glasses, they use toughened glass. Okay, I am not going into detail of the toughened glass, but what I can say, the toughened glass, as you see, the crack propagation is not like a, it doesn't follow the straight line, rather it goes zigzag. Okay, so this is a toughened glass. And in case of crystalline material, as I said, there could be single crystal material. So in case of single crystal material, we have minimized the defect. But in case of polycrystalline material, if crack follows the grain boundary, what you can see, crack actually is going in a zigzag way, isn't it? So that is how, if it goes straight line and if it goes zigzag, as you can see, the path length has significant difference. The path length for composites will be much longer, but for path length for glass will be much shorter. And moreover, one of the toughening mechanism is, if you somehow can deviate the crack tip, then what happens? Crack velocity will be reduced drastically. Crack velocity will be reduced drastically. So that is our role to play, how to design the material so that crack tip doesn't follow the straight line, rather it follows zigzag. Not only that, at the crack tip, is it possible somehow to develop the compressive force so that it doesn't grow? If it is under tension, it will grow. Have you ever seen cements or the concretes are used under tension? Usually not. It is under either used under mixed mode or it is under compression. I think we know the famous ad of Ambuja cement. So very high compressive strength. It doesn't say very high tensile strength. Okay. So concretes, bridge, always used under compression, not under tension. Is it clear? And so we are designing the material in a way that crack tip doesn't follow the straight line. It follows zigzag. As they deviate from straight line, the crack velocity drastically reduces. Crack velocity drastically reduces, right? And eventually you get longer time for the failure to happen. So one of the example of this crystalline material, as you can see, the crack doesn't follow the straight line, and here you can see one is a black phase, another is a very bright phase, which is bright one is zirconia and black one is alumina. And here directly you can see there is a toughening mechanism, and that is why the crack doesn't follow the straight line, it follows zigzag. So now our job is to design the material or other biomaterials in a way that under cyclic loading and unloading conditions, the crack should not have catastrophic failure. Rather, it should have some time for failure, as well as it should actually have some toughening mechanism so that crack tip doesn't grow at the velocity of sound. So this is one of the mechanism. So deflection of the crack path thus increases in crack length. So if you can deflect the crack path, then it has to travel longer length. So eventually it will take longer time to reach to the edge, so that material will fail. Similarly, as they deflect, the reduction in stress concentration at the crack tip. At the deflect, there will be reduction in stress concentration at the crack tip. Similarly, so you design the material in a way, even if crack has propagated, there are components which is actually bridging. So this is the case for fiber matrix composite. So I can have fiber which is strongly bound to the matrix, or I can have fiber which is having weak interface with the matrix. So which one is the better one? Can you tell which one is the better one? So as you see here, the crack follows the straight line, and you see because this fiber and the matrix has weak interface, so it doesn't go straight, rather it follows the weak interface and it deviates. So as it deviates, we are actually able to deflate the crack path, thus increases the crack length and reduction in stress concentration at the crack tip. Secondly, some of the fibers you can see it is pulling out. So this pulling out meaning it is actually releasing more surface. So eventually it involves more stress consumption. So that is also a toughening. Similarly, there are some fibers which break down. For breaking down also you need extra energy. So that also acting for toughening of the material. Similarly, in case of platelets. So you can see some of the platelets break down. Some platelets are still acting like a bridge, and some platelets here you can see the crack is propagating through. Okay, even some platelets also can have some crack deflection because of weak interface between the platelet and the matrix. Okay, and there is another mechanism called fiber pull out, already I mentioned, and there is another mechanism that when the crack is propagating under the stress, so at the crack tip there could be small micro cracks. This micro cracks eventually reduces the stress concentration at the crack tip and thus toughening. This is one of the mechanism of toughening in case of zirconia as well as in case of bone or dentures. Okay, we will see later on. So here I can see one of the particulate composite, and very nice example. What you can see here, in this particulate composite you can see one of the big grain, and in this big grain crack actually follow almost straight line for some time. This is not desirable. So that is why when you are designing the material you need to control the grain size. So grain size should not be very big or grain size should not be even very small. Okay, so there should be optimization in terms of grain size distribution, average grain size distribution. One of the example is alumina zirconia composite, where average grain size is preferable of about 0.5 micron. Similarly, you can see there is another microstructure. You can see there is a fiber pull out and there are some fiber breakdown. Okay, so these are all different fiber matrix composites toughening. Okay, so crack deflection mechanism. I think now we know very well why and how mason uses this kind of brick building what do you call techniques. So I remember in my childhood, the mason, while they're making the walls, they're breaking actually intact brick, they're breaking. So I was not very happy actually, why they're breaking the bricks. But today I understand why they're breaking it, because they're intentionally doing such intercalated structure so that the crack can deflect, it doesn't follow the straight line, right? Similarly, as you see in the down, there is another picture. So you want to join the two walls, would you follow this mechanism or would you follow the other mechanism? So it gives you the answer. So similarly, as I said, last 30 years of implant failure analysis says that failure happens at the interface. So we have to think about how mason does, what they are doing at the interface. So we need to think about a material which will have highly interconnected porous structure or bony tissue can grow into it, so that there is no very sharp interface, rather you have kind of zigzag interface, and huge amount of material and huge amount of bone, they interact with each other and load transfer will be very gradual. There is no sharp load transfer, and that gives you toughening. So now if we go through the strength versus density graph, I should acknowledge here this diagram is done by very famous Asby. Okay, so this is, I think, his style, I can say. If you see all his books, everywhere. He's always trying to take the data from different literatures, thousands or millions of literatures, and he's just putting the dots. And he is trying to see the trends. What you can see here, the ceramics strength is the highest, and the glass, metal and alloys are here, and glass has very small window, whereas the composites, it starts from much lower values, it goes to much higher. The same materials, if you make it porous, the foam which comes here, strength is much less. And as you know, the woods and polymers are in between. Okay. So as we see the strength versus density drawing, ceramics is much higher. Then it comes composite, metal alloys. Then you have polymers, and you have porous ceramics, and you have foams, and you have wood products. Similarly, there is another diagram also by Michael SB, the Young's modulus. As you see the Young's modulus, what you see, ceramics has the highest modulus. So ceramics had the highest strength, now ceramics has the highest modulus. And also you can see the metal alloys also has very high modulus. But as you see the polymers, foam and wood and the composite, so here you can see there are different Young's modulus. So you need to choose the material while you are going for replacing the tissues with the materials or implants. So you need to consider these two factors, strength as well as modulus. But as you see that, we will see later on that actually the synthetic materials like specifically ceramics and metals has much higher strength and modulus than the native tissues. And eventually, as you know, the stress shielding is the major key that refers to the reduction in bone density or osteopenia as a result of removal of normal stress from the bone by an implant. For instance, the femoral component of the hip prosthesis. So Wolf suggested that if the implant is actually in under unloading condition, there will be osteolysis or bone resorption, that also a mechanism of implant failure. So based on all the processing, structure, property and performance relationship, we need to choose the right material for the right job. Right material for the right job. So let us see how nature work. So as you see, the coccolith is a calcium carbonate formed by coccolithopores, single-celled algae such as Amylenia huxleyi. So coccolith has calcium carbonate and it is almost defect free, and that is why it has enormous strength. Similarly, you see like nacre, which is a platelet like structure, and in between the platelets there are proteins. These proteins are acting like a shock absorber, and these platelets are intercalated, and that is why the crack doesn't follow the straight line, rather it follows zigzag. Similarly, in case of sea urchins, we know they use, I think, calcium carbonate, and some of them diatom they use the silica, and these are usually single crystal materials. So as they are single crystal, the defects are minimized and they are also having enormous strength. Similarly, as you see the dentures, this is the cross section of dentures. As you see here, so after leaching with the phosphoric acid, so there are collagen fibers which is visible, and also there were minerals. So this is a hybrid matrix composites where fiber reinforcement and fiber is also matrix. Similarly, there is another material which is spider web, right? Spider web. I think, as you said, this is the strongest material on earth. Why it is? Because its feature size is much finer. So defect size, I remember that fracture toughness directly proportional to square of crack length, not square, square root of crack length. So crack length here will be much smaller, defect size is much smaller, and that is why, so this material is very strongest material. Similarly, so these spider webs also has two type of fibers. One is adhesive fibers, another is non-adhesive fibers, and there are some coils. When predator comes or some some insects jump on the what you call these webs, and this coiling and uncoiling mechanism actually saves the what you call the web from the tearing. Similarly, we know tendon, ligament. Tendon in ligament also has that kind of folded structure, and when you are stretching, they unfold as you are again, so it folds and unfolds depending on the requirement. Okay, so you can see here the design is very key. So besides material, so as you can see, these materials are very simple materials, but the design are the key for their extraordinary properties, and that is why, so not only the materials but also the design has to be taken into consideration. I think already Professor Gupta and Professor Nico has mentioned a lot about design, so I am not going too much into design, but maybe in one lecture I will be talking about customization. So there I will little bit talk how we do customization in our laboratory, but definitely design is important. So now you see that bone, I think already people, I mean, lot of discussion was there. So but I'll talk about bone again. So you see the cancellous bone, and we know the cortical bone. So as you know, the cortical bone is all around. So any external what do you call shock comes in, so that will be transferred circumferentially, and then as it transmitted to the cancellous bone, so cancellous bones are like a strut, and they buckle and then again come back. So this kind of buckling and coming back actually a toughening mechanism for the bones. And as we know, bone is also piezoelectric. Bone is a piezoelectric material. We will see later on, if time is there a little bit, I will say why it is piezoelectric, because it is a hydroxyapatite which is hexagonal close packed structure, and as it deforms, there is a charge separation that eventually give you piezoelectricity. So as they are piezoelectric, so this buckling and then elastic bounce back helps. So it helps, it actually helps that charge separation, and that is actually a mechanical stimuli for the stem cells to differentiate into bone cell lineage. So that is required. Okay, and also we know the bone has extracellular matrix. They have the cells like osteoblast and osteoclast. Osteoblast actually synthesizes the bone, whereas osteoclast actually eroded the bone. So it actually dissolves the bone. So that balance between osteoblast and osteoclast is actually helps for bone remodeling and bone synthesis as well. And there are bone marrows. Bone marrow has hematopoietic stem cells, mesenchymal stem cells, as well as endothelial cells. Hematopoietic stem cells is a source of all type of blood cells like red blood cells, white blood cells, platelets. Similarly, mesenchymal stem cells also helps to supply the cells wherever there is a demand. Okay, and these mesenchymal stem cells can differentiate into bone cell lineage for remodeling of the bone as well as for the cartilage. So this is a I think very famous diagram. I think it is given by Molly Stevens. I forgot. I think anyway. So it is published in some Nature papers as well as yeah, it is published in Materials Today here, and also it is published in some other paper. From there they have referred. Anyway, so as you see the bone, if you see the microstructure of the bone, so there is a complete hierarchy. There is a complete hierarchy, nano to micro to macro, right? So as you see here, the bone has a collagen which are unidirectionally aligned, and between the two collagen molecules there will be gap of about 45 nanometers, and at the end of this collagen molecule there are different proteins, phosphoproteins, phosphorylated proteins, osteopontin, osteonectin, bone silo-protein. So these proteins are actually the template for mineralization. They start mineralizing from at this point at the end of this collagen, and because there is gap of about 45 nanometers, so there will be a unidirectionally growth of hydroxyapatite crystals. So eventually it gives you a composite of hydroxyapatite and collagen, and as you see from osteon, each and individual layers, the collagens are oriented at different directions. So that gives you cholesteric kind of cholesteric fashion rearrangement, and it gives you some kind of toughening mechanism. And as you know, the bone cells are attached to the extracellular matrix, so they are actually adhered to the collagen, has RGDQs, and cell surface has integrin receptor. This integrin actually adhere to the collagen. So basically, as you see, the starting units are much smaller and much finer. So the defect size is actually much finer. As defect size is finer, so material is stronger. Though even you started with single and very maybe simple material, it's not a simple material, but maybe a simple material. So that is one of the important factors. Similarly, in case of cartilage, there are different zones. So one is subchondral layer, calcified layer, and there is a middle zone and superficial zone. And at different layers, collagens are arranged in different directions, and of course here you find lot of collagen 2 and proteoglycans. These proteoglycans, they are actually in a hydrated condition and they act like a shock absorber, and as they are confined between the protein and the collagen layers, these collagen are actually hydrophobic in nature. So that is why the water remains with the gags and it acts like a shock absorber. And most importantly, in case of cartilage, there is no blood vessels, and that is why if cartilage has some kind of degradation, it takes much longer time for regeneration, and that is why we go for hip as well as knee surgery, specifically in case of osteoarthritis. So as I said, so collagen has hierarchy structure, nano to macro, and as you see here, there is a micro crack formation because of this collagen folding and unfolding, and there is a continuity of collagen molecules, and there is a bridging, as well as there is osteons. They also helps in crack deflection. So altogether, so collagen, bone is a wonderful composite, hybrid composite, and it has all sorts of toughening mechanism, right? So when you are going for replacing bone, we have to mimic such material. We need to augment this kind of toughening mechanism in the material so that it works wonderfully. Besides this, it has to be bioactive, so the cell has to adhere. So then I am adding more and more functions into it. So now let us see the materials. So here I have given quite a lot of materials. You can say articular cartilage modulus is 0.000145 psi. PTFE, polytetrafluoroethylene, modulus is 0.07 psi. Bone cements 0.44. Bone has, of course, it has a range. Alloys, we can see alloys has very different type of modulus, and ceramics has the highest modulus. Okay. So we need to now think about how to mimic such kind of materials and to mimic the native tissue function and the tissue property using these kind of synthetic materials. It is a very much challenging job. So I think I am not going into detail of this material, but just here I would like to mention that not only to mimic the structure, but also while we are designing such implants, I think already Professor Gupta, Professor Nico, as well as doctors, couple of doctors suggested that we have to go for ultramolecular polyethylene, you have to go for ceramics, you have to go for titanium. Very much confusing, isn't it? So where the titanium is, where the ceramics is, and where the ultramolecular polyethylene is. So unless we know the materials property, unless we study them, and for specific applications, we cannot predict their structure, function, and specifically their permutation and combination. Okay, what permutation combination is the most appropriate for the most suitable application. Okay, here I can see one of the femoral head, femur. So here you can see there is a hydroxyapatite coating and there is a ceramic ball on titanium alloys, and here we can see metal on metal, ceramic on ceramic, metal on polymer, or there could be ceramic on polymer, but I would never see that ceramic on metal, because ceramic is really hard and it actually wear out metals, and there will be a lot of debris particle which will be exposed to the local tissues, and eventually it triggers the osteoclast activities and osteolysis, macrophage activities and osteolysis. So as I said, so design is the key, and here I can see there is ultramolecular polyethylene, and there is a titanium mesh cup, and there is a titanium stem. Okay, so we need to decide which material to go for what application. Okay, so I can end here this talk. So I'll go for the next session. So I think again I would like to acknowledge figures, tables, and results presented here are taken from different literatures, different company websites, as well as research articles. So it is for only teaching purpose, not for commercial value. Okay, thank you very much. আচ্ছা আচ্ছা ঠিক আছে। টাইটেল হবে না বলছে, টাইটেলটা বাদ দিয়ে দিচ্ছি। টাইটেলটা দিচ্ছি না, তাই না? মাইক অন করা আছে, ব্যাটারি শেষ হয়ে গেল না? নাহলে এবার ঝড় বয়ে দিবি। হ্যাঁ হ্যাঁ ঠিক আছে। এনে না হলে বুঝতে পারবেন না, এগুলো খুব কমপ্লিকেটেড জিনিস এগুলো। তাহলে মেটেরিয়াল সায়েন্সের মানে গ্রামার। এক্স্যাক্টলি, ঠিক ঠিক আছে। So good afternoon. So again we are continuing with the same topic. So let us see the examples of different ceramics which are used for the medicine. So one is alumina, which is used for joint replacement, dental implants; zirconia, which is also used for joint replacement, dental implants; calcium phosphate, which is used for bone repairing, augmentation, surface coating on metal. It's like bioactivation. Insoluble glasses like carrier for enzymes, antibodies. Nowadays people are also using the glass for drug delivery application. Glass also used as a coating. So bioglass or bioactive glass is used for soft tissue adhesion, even for bone replacement. Porcelain is used for dentures for long time. In recent time people are working, or even already some of the products are available in the market on lucite lithium disilicate based glass for dentures. So there are some machinable glass available for machining into customized shape for specific application, including dentures. Of course, carbon is a unique material which is used for very soft tissue application, as well as even for very hard load bearing applications like diamond like coating. Okay, that is used for load bearing applications. So as I said, alumina is aluminium oxide. So usually alumina or aluminium oxide, alpha alumina, so alumina has about 17 phases. So out of that, alpha alumina is the most stable phase and mechanically superior. Alpha alumina is used for joint replacement and dental implants, even for nails, pins. So what we can see here, this is again this diagram is given by Larry Hench. I think we know the Larry Hench by now. Larry Hench is very famous for introducing bioglass. I think Larry Hench's bioglass is the genesis of biomaterials field. I consider that as a starting point of biomaterials research, because 1969 onwards, I think people started thinking to use bioactive materials for this kind of implant application. So you can see here, I will not talk about many materials, I will be limited to only few, so that way it will be much easier. So you can see alumina, you can see hydroxyapatite, which is the minerals phase of the bone, bioactive glass ceramics, bioactive composites, alumina, hydroxyapatite PLA, which is polylactic acid composite, dental implants, which is alumina. So maxillofacial reconstruction, alumina, hydroxyapatite, hydroxyapatite PLA composites are used. Even polymer also is used. Some of the polymer foam, porous polymer is also used. As we know that alumina is bio-inert. So what is the fixation mechanism? Tissue ingrowth and morphological fixation. Tissue ingrowth and morphological fixation. So it doesn't adhere to the bone or tissues. Eventually, I think in 2004 or 2003, there are some reports, independent reports. Some report says alumina is bioactive. So they have done some kind of treatment and they are able to make alumina bioactive. There are some other reports. I think it was from Netherlands. Exact, I think University of Twente. It was published in Journal of Materials in Medicine. So they said that alumina cannot be bioactive. But finally, today people are able to make alumina bioactive as well by doing proper surface treatment. I think our group in University of Bristol, so one guy is a PhD student, Singh. So he was boiling the alumina with hydroxyapatite and he was able to make the bioactive. So basically, if the alumina surface have lot of OH by boiling with sodium hydroxide, so this OH will be the nucleation site for calcium, and eventually as you dip into SBF, okay, so it can have bone growth on the surface of alumina. So hydroxyapatite, we know it is bioactive, and hydroxyapatite is also not resorbable. It is almost inert, it doesn't resorb, it doesn't degrade, whereas alumina also doesn't degrade. So these are used for permanent implants, but hydroxyapatite has very poor mechanical properties. So mostly hydroxyapatite is used as a coating on the for making bioactive surfaces, and hydroxyapatite is not used for load bearing applications because it has a very poor mechanical properties. So hydroxyapatite will have catastrophic failure if it is used for load bearing applications, but it can be used as a composite with PLA, polylactic acid. Lactic acid is a polymer which is a hydrophobic polymer, and polylactic acid hydroxyapatite composite would be good for bioactive bone graft application. And as I said, alumina is used for maxillofacial reconstruction, where morphological fixation, the Halbert concept, not the Larry Hens concept, Halbert concept is used for morphological fixation, and because it is not for load bearing applications, just tissue will grow into the pores, and that is how it integrates with the tissues. Dental implants, so alumina is used as a dental implants. Even zirconia is also used as a dental implants. Alumina zirconia composites also used as a dental implants. So here I would like to mention that while I used to work in University of Bristol Dental Science, our landlord, so once he asked me, oh, you work in the dental science, and as you see my the lower jaw dentures replaced with a synthetic one, and upper jaw dentures has gone because of this what you call relative motions. So wear and tear has happened on the upper jaw because the synthetic implants were much what you call hard, and eventually as it was rubbing against the natural teeth, and natural teeth has wear out. So that is why while you are choosing the dental implants materials or such type of applications, we need to choose the material which should be compatible to the specific conditions. So that is why even if you use the alumina as a dental crown, I think I specifically mentioned because you already said that you work on dental implants, so you have to choose a coating on the surface of these dentures. I think I can show you. So this is one of the dentures we have developed back in 2000, I think 11 or 12, and we also filed patent on this process jointly by Dept and IIT Kharagpur. And you can see this is the alumina dentures. right? This is alumina dentures, and on these dentures we have a coating on the surface. You see, surface coating is there. So this coating, which is a glass coating, and this coating has the property very similar to dentures, so it doesn't damage the native dentures. So you have to take into consideration about that. But as we know, while you are chewing, the dentures actually flexes, bends. So if you have alumina as a root, eventually break down. So that is why we need to choose a root which has certain amount of flexibility. So you can use titanium, right, or you can use some composite which can allow you to have some kind of bending mode, okay, bending mode of operation. So here this crown will be placed on the top of the root, and this root, as it is going inside the mandible, so there is a mandible here, as you can see, this is a mandible, right, this is the mandible. So you drill and you place the root, and this root has to bond to the bone. So that is why this root has to be bioactive. And I mentioned to you, Johnson and Zimmer has introduced a new dental root in 2013, and that has some part of cancellous-like structure that allows the bone ingrowth and bone ungrowth, and eventually osteo incorporation that helps much more complex load. And you are placing this root, sorry, this crown on the top of the root. Okay, this is called implants. So implants are very rarely available in our country. We mostly go for bridges, like the existing dentures we clear and we make the post, and on the post we actually put the cap. Okay, is it okay? So there are hydroxyapatite PLA composites, tricalcium phosphate, that is another important material, TCP, tricalcium phosphate. So tricalcium phosphate has much higher resorbability than hydroxyapatite. So if you can use the tricalcium phosphate in combination with hydroxyapatite or OCP, octacalcium phosphates also has some resorbability. So this can eventually give you some sort of resorbability. So for the implant where you want some kind of remodeling, so this TCP and OCP, if it is there along with the hydroxyapatite doesn't dissolve easily. But as the TCP and OCP dissolves, there is a increase in local concentration of calcium and phosphadions. This calcium and phosphadion again reverts back as a minerals, and then eventually give you faster bone growth. So hydroxyapatite, bioglass and bioactive glass ceramics, tricalcium phosphate, alumina and zirconia. So these are the materials which are mostly used for different applications, and in recent time, as I said, leucite, lithium disilicate also used for dentures application. And also there are different type of glass, right, and where in this glass they are doping different type of elements, strontium, copper, cobalt, nickel, just for different purposes, even zinc. So zincs give you antimicrobial property, silver give you antimicrobial property, gold give you antimicrobial property. Similarly, cobalt or strontium gives you, can you tell me what? Strontium, copper also can give you some angiogenic property as well as some antimicrobial property. So it helps for blood vessel formation. Strontium, copper, cobalt, now people are working on that. If you just go through smallest events from Imperial College London, see he is doping different type of minerals in the glass for angiogenesis, right? And also there is another class, metals. I think we know that there's a lot of history on stainless steel. 304 stainless steel, then 316 stainless steel. Before that 302 stainless steel. Then we have 316L stainless steel. And I think it is used a lot even today. This is the implant which is available from our country. Einor Orthopaedics. I think I purchased quite a lot of implants from them just for demonstration. So this is made of stainless steel. So I think today we say that okay, titanium is a very state-of-the-art material for bioactive implants, but even today also in our country we get these hip implants. What is the cost of these hip implants? 5,000 rupees only. We spend 5,000 rupees only. So that is it's worth mentioning. Just 5,000 rupees one implant. It's Mumbai based company. Anyway, so just to mention that, so stainless steel is also used, and it is, I think this is one of the rare of the rarest company from India. They make still these kind of implants. So as you know, most of the implants are available from abroad, but this is Indian company. They're making for some time now. Pardon? Einor Orthopaedics. Einor Orthopaedics. Okay. They have hinge joints, hip joints, knee joints, nails, plates. Okay. So 316L stainless steel. It is used for fracture fixation, even stent and surgical instruments. So commercially pure titanium, titanium 6 aluminum 4 vanadium Ti64, titanium aluminum niobium, titanium niobium zirconium, titanium molybdenum zirconium iron. So these are different implants are also used for bone joint replacement, fracture fixation, dental implants, pacemaker, encapsulation, etc. So cobalt chromium molybdenum is also used as an implant specifically for femoral head, joints replacement, dental implants, and heart valves, where the ring is used of cobalt chromium or cobalt chromium nickel. Nitinol. This is very important material. Anybody can tell what is the property of the nitinol? Very special property. Safe memory alloy. So safe memory effect was discovered in 1950s or 60s I think, and it is used for dental archwares. This is one of the finest application, and of course stent, orthodontic archwares, bone plates, and stent, and of course catheter. Very smart catheters are available where we can use for different surgical interventions. So nitinol safe memory effect is utilized for different purposes. Gold alloys, I think no more used. Still we see Tinuanant who is laughing with our gold dentures. Okay. Anyway, so dentures are used for gold alloys are used for dental applications. Silver is also used for antimicrobial agents. I think we have a very long tradition of rings where we use 8 different metals. I remember one of my friend, my colleague in University of Bristol, he used to criticize me that he used to mention, oh, you Indians eat by hands. And I used to say that you are Nottingham University, I saw the literature, some Indian, they did the research. They said if you keep the water in the copper vessel, so there is a reduction in bacteria concentration. But whereas if you keep the water in the plastic container, the bacteria concentration increases. And I give the logic. So we have the finger ring, right? And it has 8 metals, silver, gold, and all these. As you rub against the metal container, like stainless steel, so you get the nanoparticle into it, and you get the antimicrobial efficacy, right? So you have to find some positive as well. Okay. So definitely silver, gold, and I can tell you one more thing. I should switch off. Yeah, so so today, if you see 2005-6 onwards, if you see there are many patents on wound dressing material. They are using the same dressing, just they are saying, okay, there is a silver nanoparticle, there is a gold nanoparticle, there is a platinum nanoparticle, there is a zinc nanoparticle, and they have enhanced antimicrobial efficacy. Even sometimes you see that there is a refrigerator, there is a silver nano. So now people are trying to add more functions on the products so that you can have more efficacy. As I said, wound dressing material. So just people are using silver nanoparticle to have antimicrobial properties. And I think this mercury, silver and tin amalgam is no more used for dental restoration. And of course, there are polymers. So there is a huge number of polymers which are used for biomedical applications. So as you can see here, I will just read out some of the polymers. CF, which is carbon fiber. C is carbon. GF is a glass fiber. KF is a Kevlar fibers. Kevlar is also used for bulletproof jacket. PMMA, polymethyl methacrylate, is used for contact lens, intraocular lens, IOL lenses, as well as for glass and bone cements. Polysulfone is used for blood dialysis, blood purification membrane. If there is a kidney failure, polysulfone membrane is used for blood dialysis. Polypropylene, ultraemulsified polyethylene, which is mostly used for load bearing applications. PLDLA, poly-LDL lactic acid or lactide. PLLA, poly-L-lactic acid. PGA, polyglycolic acid. Polycarbonate. PEEK, 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 polyether ether ketone. Polymethacrylate. BIS-GMA. So BIS-GMA is used as a cross-linker for dental fillers. Polyurethane, PTFE, polyethylene tetra, a polytetrafluoroethylene, which is used for blood-related applications. PET, polyethylene terephthalate, it is also used for making fibers for blood-related application. PEA, polyethyl acrylate. Silicone rubber has lot of applications specifically for cosmetic implants, and it is having lot of blood compatibility, good blood compatibility, and so it is used for some catheter application also. So a silicone rubber is also used for facial reconstruction as well. PELA, a block copolymer of lactic acid, polyethylene glycol, liquid crystalline polymers, polyhydroxybutyrate, polyethylene glycol, polyhydroxyethylene methacrylate. This is used for hydrogel lenses, okay, and also transdermal drug delivery systems. So as you see here, this is the application of silicone rubber. Different application of silicone rubbers. Polylactic acid is used for stent, sutures. Polyglycolic acid is also used for sutures, biodegradable sutures, and polylactic glycolic acid is also used for biodegradable sutures, drug delivery systems, and nails or pins, bioresorbable pins. I think I will come in detail later on. So as we categorize the polymers, so polymers are biodegradable polymers, polymers are bioresorbable polymers, polymers could be bioerodible, and polymers could be bioabsorbable. I am not going into detail of these classes, but you just remember there are bioinert polymers, there are biodegradable polymers. So bioinert polymers are used for load bearing applications as a permanent implants, whereas biodegradable polymers are used as a transient implants. So similarly, we will see there are some compositions of ceramics, there are some compositions of metals, these are also biodegradable or bioresorbable. As you see the timeline, 1950s, the first generation biomaterials, 1950s and 60s, first generation biomaterials. So people used to think about inert biomaterials. And then 1970s, 80s, bioactive or bioresorbable biomaterials, where bioglass, hydroxyapatite, and then collagen and other biodegradable polymers came into the picture. And then in 2000 onwards, there are different bioactive and bioresorbable biomaterials. Today we have biomimetic biomaterials. Okay, we have biomimetic biomaterials, and today we are conceptualizing to print or to develop the functional tissues in the laboratory, which can be replaced by the native tissues, and it works like a natural tissues. So if you see, there are bio-inert implant, bioresorbable implant, and bioactive implant. And I already mentioned before that bioactive implants are the implants where we have specific chemistry that will be beneficial for calcium nucleation or phosphate nucleation, and eventually phosphate nucleates on the calcium side or calcium nucleates on the phosphate side. And then there is a nucleation and growth of bone by a biomimetic biomineralization approach proposed by Kokobu using simulated body fluid. But now I would like to mention that there are certain cues like RGD, arginine glycine aspartic acid, then YIGSR, IKVAV, LRE, REDV. So these are different small peptide sequences, and that are recognized by the cells. So a perfectly inert material, if you just somehow adhere these kind of materials, these kind of cues on the surface, they behave like a bioactive materials. The materials which is worst for cell adhesion, it becomes bioactive or excellent material for cell adhesion. So that is why today people are working on bioactivation or bioactive materials development via biomimetic approach. Okay. So you can see fibronectin, vitronectin, laminin, collagen, fibrinogen, thrombospondin, enactin, and tenascin. These are all has RGD cues. Similarly, laminin has many different cues, and laminins are abundant in basement membrane, I mentioned yesterday. So that is why laminin is also a wonderful adhesion molecule. It can adhere to the proteins, it can adhere to the glycosaminoglycan, proteoglycans, and also to the cells. Then you can see here alumina has a compressive strength of about 4000 MPa, and bone has the and Young's modulus is about 400 GPa. I think I extensively worked on alumina during my PhD days, and alumina is a very strong material definitely, and it has Young's modulus is about 360 to 400 GPa. Zirconia, see PS, partially stabilized zirconia. Zirconia has fully stabilized zirconia, you have partially stabilized zirconia. So zirconia has Young's modulus about 150 to 200 GPa, and it has compressive strength of 2000 MPa. I think it could be even higher. And hardness, if you see, hardness of alumina is 2000 to 3000 Vickers hardness value, and zirconia has 1000 to 3000 hardness value. Whereas the graphite has much low Young's modulus and compressive strength. So bioactive glass or bioactive hydroxyapatite has even lower Young's modulus, compressive strength, Okay, and whereas if you see the bone has much lower Young's modulus and compressive strength. So as you said, when we are going to use the material for replacing such native tissues, we are not able to match the modulus as well as the strength. So we have to consider the design aspect as well to address this issue, stress shielding issues. So here, as I said before, again I am mentioning here. So here, functionally graded porous implant is the key, and you can see here Zimmer has developed these dental implants. You can see the surface has porosity. This porosity and pore size and the surface texture helps for bone on growth and ingrowth, and osteo integration and osteo incorporation. Okay, so modulus has to be matched by making it porous and gradual load transfer, and we have large interfacial interaction, and because the pore size is more than 100 micron, we have blood supply and we have bioactivity, and eventually we have osteo incorporation, and this hierarchical porosity and roughness is beneficial for cell adhesion, blood vessel formation and tissue ingrowth. So here you can see from EDX studies that how there is a bone ingrowth into the implants. So bright one is the titanium and the gray one is the bone, and you can see from optical image how the bone has nicely grown into the porous implants. This is from Zimmer database, and you can see from optical image of how bone looks like on the top of metal, porous metal, and this is a micro CT of interface where you can see bone and implant have very nice intercalation. That is important for longer survival of the implants. And this is a cartoon where this bluish part is the metal and the brownish part is the native bone, and they are intermingled, and that is how the load transfer is gradual to avoid the stress shielding. So this is very important. Bioglass, as I mentioned, 1969 is the breaking point. Okay, so I think 1960s Vietnam War was there. So Larry Hench, just after graduating from ceramics, he joined as a faculty at University of Florida. I visited his lab as well as I have attended his retirement meeting. So that time I used to work in University of Bristol. So in his retirement meeting, I was there. So he was mentioning the story of bioglass, even if it's also published in a couple of journals. So what he mentioned is, so while he was consulting with the doctors, doctor mentioned that it is very easy to save the life, but it is very difficult to save the limb. So what was happening is, the limb was, to save the life, they had to remove the limb. So then he was discussing with Larry Hench, can you develop a material which can act like a host, which can act like a native tissues, and it can adhere to the native tissues? So that was the starting point to think. And as he was extensively he was having knowledge of glass. He was from ceramics, but according to his word, somehow he somehow did not think or forgot about the bioglass silica phase diagram. And as he discussed with the doctor suggested that in the bone you have calcium and you have phosphate. So he randomly mixed some silica. As you know that silica is bioactive or bioinert or biotoxic? Toxic. So its isoelectric point is 4. So periphery of the silica, all cell will die, tissue will die. But what he did, he mixed the silica with calcium, sodium and phosphate. So he has arbitrarily chosen a composition which is having 6% phosphate, 24.5% calcium oxide, 24.5% sodium oxide and 45% silica. And that composition, he made the glass, and I think I have gone through some of the journals, cartoons, and doctors are jumping in the farmhouse. That one composition which is doctor is trying to pull out, it's not coming out. So that was the starting point. So they developed a glass which are able to bond to the bone. So today we know, I think I will go through some of the tables. We will show that many different type of bioglasses are there and many companies are there. And interestingly, this specifically the 45S5 bioglass R, this what do you call this trade name. So this glass can be bonded to the soft tissues within 24 hours. I think within 8 hours. If I think it is within 8 hours, it can be bonded to the bone. So you can see there are different type of bioglass available, and you can see the bioglass. So this is the phase diagram of bioglass. This is the phase diagram of bioglass. This is the phase diagram of bioglass, and this is called trinary phase diagram. Okay, you have, I think I should not go into detail of phase diagram, there will be problem. So rather I avoid, just to mention, you have silica 100% here, you have calcium 100% here, and you have sodium 100% here. And if you are here 50% calcium and 50% silica, and you have here 50% silica and 50% sodium, and here you have a composition where 45% silica, 24.5% calcium oxide, 24.5% sodium oxide, and you see the dotted line. Within this dotted line, this glass has wonderful property, not only bonded to the bone, but also it can bond to soft tissues. So you can see here that class A bioactive material. So if you see here, you see IB is bioactivity index. IB is bioactivity index, and if you see the IB is equal to 10, the number says 10 meaning highest bioactivity, meaning it's actually having highest bioactivity and much faster soft tissue adhesion as well as bone adhesion. And then you see the bioactivity index reduces within the dotted line, it is 8, and then it is bioactivity index is 5, then you have 2, then you have 0. So in this area, which is very rich in this silica, so as we know that silica is toxic, so that is why the zone B, I think here in these two pictures little bit different. So here zone B is, here it is zone C. So zone C is bio inactive, whereas zone D, here is zone E, is non-glass forming, because silica is a very long chain, covalently bonded, alternate silicon oxygen silicon oxygen silicon oxygen network, and this single valence ions, cations, they work like a network breaker. They break down this SiO-Si bond and they comes in between. So that is why if you have too much of sodium into the glass property will not be there. It doesn't form a good glass. Okay, so that is why it's a non-glass forming material, because you have too much of sodium, right? And D, zone D, you see you have a lot of sodium and you have silica, but calcium is very less. But as you know, the sodium oxide or sodium chloride, if you put in water, what happens? It dissolves. So this glass is a composition where you see that dissolves. So this glass composition is bioactive, but also it dissolves away. This glass can dissolve away. So if you have good combination of bioresorbable glass and bioactive glass, depending on health of the tissues, if you can match the tissue regeneration property with bioresorbability, you have done a good job. So that means the tissue growth kinetics matches with the degradation kinetics. So slowly the materials will degrade away and tissue will grow and fill the gap. Is it clear to everyone? No issues? So what you see here is the mechanism of bioactivation or bone growth formation. So as you dip into the body fluid, so water or body fluid interacts with the material, and there are silicon, oxygen, sodium bonding is there, and there will be quick ion exchange of sodium and potassium with H plus and OH. So there is formation of SiOH bonds, and these SiOH bonds will form, and also there are some SiO-Si bonds which also break down into SiOH. Okay, this is in the second step it happens. I mean, these are the sequential events. So there are some ion exchange, there are some silicon SiO-Si bond breaking, so eventually gives you SiOH, and also SiOH bonds combine together forming SiO-Si bonds. And this free SiOH group acts as a nucleation site for calcium, and once the calcium come in, the phosphate also come in. So as you can see here, then calcium start nucleating on the surface of SiO minus, and then phosphates come in, and there is a nucleation of calcium phosphate and eventual growth of hydroxyapatite or hydroxyapatite carbonate or phosphate like layers on the surface of the material, and that is what is bioactivation, similar to Kokovo's method. Okay, so in case of bioglass it happens. So here I can show you, I'd like to show you that there are different type of compositions for bioglass. What you can see, 45S5 bioglass, there are 45S5 4F bioglass, 45 B15S5 bioglass, 55S. So this 45, 45, 15S or 52S and 55S, these stands for silica. 45% silica, 52% silica, 55% silica. Okay, there are glasses like Ceravital, KGC, KGS. So these glasses all are bioactive glasses, and in recent time you will see that different groups are doping different type of ions like strontium, cobalt, copper for improved angiogenesis. Titanium, recently one paper came to me for review, just I think two weeks back. They have added the titanium, and they says that there is an enhanced angiogenesis. Similarly, the silver, platinum, gold, zinc, they add for antimicrobial efficacy. So now people are trying to add more functions on the glass, right? So you can see here the comparison of interfacial thickness of reaction layer for bioactive implants or fibrous tissue of inactive bioceramic in bone. So what we can see here is the bioglass has interfacial thickness, okay, interfacial thickness is okay this much, and it depends on the bioactivity of the material. And we know that for alumina there is a fibrous tissue formation, whereas for bioactive glass there is a tissue adhesion and tissue growth on the surface of the material. So this is very interesting. So as you know that there are many different type of calcium phosphates available, and you'll be confused to see that literature, somebody says OCP, somebody will say TTCP, somebody will say TCP, HCP, HA. Okay, so you should not be confused. So that is why I put in one slide so that you can understand very easily. So TTCP or TETCP is actually tetra calcium phosphate, and calcium by phosphate ratio is 2. Okay, and similarly in case of TCP, tricalcium phosphate, there are different phases like alpha, beta and gamma. Your calcium and phosphate ratio is 1.5. In case of hydroxyapatite, you have calcium by phosphate ratio is 1.67. So what is the implication of these? How can you use this kind of ratio for different characterizations? So if you do XRD of the implant surface after augmentation with the animal for some time, or after SBF treatment for some time in vitro in a beaker. So once you have this implant surface, you do the EDX. When you do EDX, you get the peak for calcium, also you get the peak intensity for phosphate. And if you get the area under the concentration for calcium and the phosphate, and if you get the ratio of very close to 1.67, what you can say? Is it hydroxyapatite? You should not say the hydroxyapatite, you said that hydroxyapatite like composition is there. Unless we do XRD and get the specific peak, specific phase for hydroxyapatite, you cannot claim this is hydroxyapatite, because you see the tetracalcium phosphate has 2, and whereas there are dicalcium phosphate is 1. So you can have different percentage of tetracalcium phosphate as well as the as well as calcium phosphate. So that is why you should be little bit concerned about. So when you are doing the EDX, you get some calcium phosphate ratio, and from that you can predict the composition. Is it like similar to tetracalcium phosphate in terms of ratio of calcium and phosphate, not in terms of phase? So for phase analysis you have to do XRD. So here you can see Seraform for dental. This is one of the interesting applications. As you know that some cases, dentures, there is a periodontal disease and dentures has gone, and we don't have enough money, maybe. So we do not, okay, we are also thinking, okay, let's be there. But once we have money, then we go to the dental surgeon, we say, can I have a dentures? And as they inspect and say that, oh, so in your mandible, wherever the dentures was there, the root, so here the mineral health is very poor. What to do? Then what doctor will do is, because even if you drill and place the root, it doesn't stay there because there is not enough mineral. So what doctor will do, they will drill a hole and they will place this kind of Seraform, and they stitch it. So after some time, here there is a remodeling and there is a healthy bone, and then you drill and just place the dental root and then dental implants, right? So again, here is the phase diagram. I am not going into the detail of that, right? So here it shows that how calcium oxide and temperature play the role for forming different phases of calcium phosphate. We know HA is hydroxyapatite, C3P is tricalcium phosphate, C4P is tetracalcium phosphate, and there are many different other phases we have seen already. Okay, so I am not going into that, but if you have to make such compositions, you have to study the phase diagram. So one of the important application of hydroxyapatite is ocular implants. So if because of some problem, you may, some person may lose their cornea. So in that case, just to improve the appearance for cosmetic reasons, what they do, they simply take a porous hydroxyapatite ball, and on the top of that they simply paint. Okay, similar to the matching with the other cornea, and then in the back they attach to the ligament, not the ligament, muscle, like, yeah, okay, muscle, so that when you have the ocular, when you have the cornea movement, so you also have the cornea implant that also started moving. So though it doesn't have much function, but at least the appearance will be much improved. So here you can see there are many different type of products available, and very interestingly, not only hydroxyapatite and TCP, but also the collagen is combined for improved bioactivation. But these different combinations are used solely to impart the different extent of bioresorbability into the implants. Is it okay? And you can see these implants, mostly they are made porous, and you can see the pore size is 100 to 200 micron, 100 to 200 micron, 1 to 600 micron macro porous, because tissue ingrowth, tissue adhesion, and biological fixation. So the same concept is used again and again. Okay. So there are different products commercially available. So I have taken from materials today. You can see this is a bioglass foam. This was developed by Larry Hange, and now still in Imperial College, I think Larry Hange student, now he's a faculty there, he's working on that. So bioglass flakes, and this bioglass has very poor mechanical properties, but it has extremely well soft tissue adhesion properties and bone adhesion property. So that is why instead of using it for load bearing applications, it is mostly used for filling the voids. So if there is a trauma or accident, or there is a osteoporosis in some points, so simply they place some of the bioglass and they stitch, and this actually joins within 24 hours, and then it starts improving the bone density, and that is how it is used for specifically for accidental trauma. So there are Cerasorf, as you see the name suggests Cerasorf, so it absorbs. So TCP, I said it has higher resorbability. Chronoase, Tepzen Putty, hydroxyapatite based material, BioOS, even plaster of Paris is used for such applications. Okay, of course not the plaster of Paris we use, so it is much higher quality plaster of Paris, but plaster of Paris is also used for, what is the composition of plaster of Paris? Calcium sulfate. So here I can show that there are dental roots and dental abutment, and you have dental crown, and on the top of the crown we have some glass coating, veneering, that is done for appearance as well as matching the property with the natural teeth. Otherwise, as you see the dentures, natural denture also goes off, wear out. And you have alumina femoral head, and also you have tibial tray, right? In case of lower part of femur, I think lower part of femur, you have also alumina based implant. Okay, and interestingly, you see the microstructure of alumina zirconia composite. Again, I am showing, it shows granular, polycrystalline, and the white portions are zirconia, and this zirconia is actually a toughening agent. This zirconia is actually a toughening agent. Okay, and I'll explain later on how it is used for toughening. And in recent time, what is the structure you see here? Nacre like structure, intercalated plated like structure. Now people are working on dentures using very soft material, but microstructure should be like this, so that it can take enormous amount of load, but it doesn't erode the existing crown. So lithium disilicate, lithium and glucide are the materials. There is a possibility to grow such kind of microstructures. It has intercalated platelet-like structure, and it can take enormous amount of load. And because of intercalation, the crack doesn't follow the straight line. Rather, it goes through zigzag, and that is giving you toughening. Okay. So here I would like to mention that we use specific composition of titanium, Ti64, different titanium implants. We use zirconia implants, alumina zirconia implants, and nitinol. So in all these cases, we explore, or we take the benefit of a special property of the materials. This is called Martensite transformation. Have you heard this property, Martensite transformation? Martensite transformation. So it is a metastable structure. It is a metastable form, and that helps the material to give you extraordinary property. So Martensite transformation is responsible for toughening of zirconia. So this was proposed by Martens, German scientist Martin, and for zirconia, transformation toughening property was proposed by Swan and Hanning. So Ti64 also has transformation toughening property, or Martensite transformation or transformation toughening as well. Nitinol also has transformation toughening. Iron also has transformation or Martensite transformation. But you have to note here, for zirconia, we get what? Enhancement in mechanical properties. It becomes very tough. For Ti64, it becomes soft. For nitinol, also it becomes soft, and for iron carbon, it becomes hard phase. So the phase we get for zirconia is hard phase. For Ti64, we get the soft phase, and nitinol we also get the soft phase. For iron carbon, we get the hard phase. Okay. So basically, when we cool down the material, okay, and if it is cooled down bit faster, so there is no enough time for diffusion of the elements. So eventually they deposits inside the lattice structure, and that transformation is actually diffusion less transformation. So instead of normal crystal structure, they have some distorted crystal structure, and that gives you some kind of extraordinary properties. So very interestingly, I can just again give you, I am now enthusiastic enough to show you the phase diagram of zirconia. Okay, so what we can see here is the temperature versus zirconia here, 100% zirconia, 0% yttria here in this point, and as you go on along the x, the percentage of yttria increases, right? So here if you go with 0% yttria, you see that zirconia has at room temperature monoclinic phase, and you have tetragonal phase, and above some 2400 degrees centigrade we have cubic phase. And interestingly, this monoclinic and tetragonal phases has transformation. If the monoclinic transform into tetragonal, there is a volume change, and also tetragonal, if it is transforming into monoclinic, there is also a volume change. If the monoclinic changes to tetragonal, there is a volume reduction, and if tetragonal changes to monoclinic, there is a volume expansion. So now if you look at the microstructure here, if this zirconia grain changes from tetragonal to monoclinic, there is a volume expansion. But what is the space for expansion? There is no. So then if you have these two grains, zirconia grains, and they have monoclinic phases, if there is a crack propagation in between these grains and they transform under the stress, and there is a volume expansion, but there is no space for expansion. Eventually they apply compressive force, and as the crack propagate and they experience some compression. So eventually they are not going to propagate through, right? So this is one of the toughening mechanism. There is another way to do. So these grains, if they are tetragonal, they can also transform into monoclinic, and there is a volume reduction, and volume reduction is not an issue. They can reduce, and eventually they give you a lot of micro cracks, and these micro cracks gives you stress relaxation or stress release at the tip, crack tip, and that is how they work like a toughening agent. So now we have either alumina or zirconia. Both alumina is alpha alumina and zirconia is a cubic zirconia. These are like a matrix. And when you have monoclinic or tetragonal zirconia, they are toughening agent, right? So what we do here, so I want a phase where we have majority is cubic zirconia or alpha alumina, but we should have some dots of either monoclinic or tetragonal or mix. Is it clear to all of you? Is it clear or it's too much confusing? Okay, so now, so that is why what ceramic engineers are doing, they actually dope some percentage of yttria. So as you dope the yttria, what you see, this phase diagram says that this tetragonal phase is coming down, even monoclinic also is coming down. So then if you can come down, cool down this material while you are processing it or sintering it, and if you can quench them, so eventually you get cubic. Along with that, you can get some percentage of monoclinic as well as tetragonal, and eventually it gives you the mixed phase, and this mixed phase has different type of toughening mechanism for imparting resistance for crack propagation. So that is what is required. Okay, so as you see here, the crack propagates and there are some monoclinic phase transform into tetragonal at the crack tip, or tetragonal that transform into monoclinic, and there is a volume expansion or contraction, and eventually gives you transformation toughening. So very interesting, but at the same time also very sad news. So I was visiting a conference, American Ceramic Society conference back in 2004 in Baltimore. So there I think one German scientist was reading his paper, and he mentioned all the implants, zirconia based implants, after 12 years all has a failure, and shortly just after 11 to 12 years all implants has the failure. So what is the cause? And what you see here, that simply you take a zirconia implant, as you go for just autoclaving, you see there are some kind of pit or corrosion type of thing. But the ceramics doesn't have that much corrosion. But what happened? What they found, that there is a phenomena called hydrothermal phase transformation and eventual microcrack. So in vivo condition, it's not like room temperature. In vivo condition is hydrated condition, and it has certain amount of water, and at elevated temperature these grains has hydration and eventually spontaneous transformation into monoclinic to tetragonal and tetragonal to monoclinic. And if the monoclinic is transforming to tetragonal, there is a micro crack formation or aging. In ceramics, if you have cracks, then eventually that crack started growing and gives you failure. So then that is how they found that we need to again use some different doping agent for partial stabilization, like to have cubic zirconia, monoclinic and tetragonal, so that we do not have hydrothermal phase transformation. In recent time, scientists are using silica as a agent, doping agent, that actually helps to avoid the hydrothermal phase transformation, but eventually you have transformation toughening. Is it clear to all of you? So this is a partially stabilized zirconia. Partially stabilized zirconia always will have certain percentage of silica or calcia or magnesia or yttria. Okay, usually 3 mole% magnesia and 3 to 7 mole% magnesia, yttria or calcia, and even now people are using silica. I think we can stop here. Okay.